Now it's possible to have the situation where we have more than one wave travelling through a medium. In this situation, we need to invoke what's known as the principle of superposition. The principle of superposition states that if two or more waves are travelling through the same medium, then the resultant value of the wave function is the algebraic sum of the two waves. So this is basically a big mouthful to say that if we have two waves travelling through the medium, we just need to add them together at every single point to find out what the resultant wave will look like. And what we'll actually see in this situation is that resultant wave. So let's have a look at a simple example of this now. Okay, so basically what the principle of superposition means is imagine that we had these two waves input as signals into a medium. So here's our first wave, which we enter into the system, and then on the same piece of string we have this other wave as well. And the question is, well, what does that piece of string look like? And what the principle of superposition tells us is, well, just add the amplitude of the wave at each point. So at 0 here, this wave is 0, and so our resultant wave is going to be 0 at 0. Let's consider the point 2. Here, this wave is a maximum and this wave is, well, just a small value. So you can see this is going to be the maximum from here plus just the small value from here. Now to round about 5, around about here, we have a negative wave here, while there's a positive wave down here with pretty much the same magnitude. So at that point, those two waves cancel each other out. And then when we've got up here, we've got a positive wave and a negative wave with a very similar amplitude. So the amplitude of the resultant wave is very low. So we can think of a few different situations. If we have two pulses travelling through our medium, and both these pulses have a positive displacement, positive amplitude at that time, then when they pass each other, the two pulses add together, as you can see in the little video, to give a pulse with a much greater amplitude. In this case, because they're adding together to give something with a greater amplitude, we call this constructive interference. Now we can also imagine the situation where we have a pulse with a positive amplitude, displacement from equilibrium, and another pulse with a negative displacement from equilibrium. Now when these two pulses pass each other, they're going to cancel each other out, and this is known as destructive interference. So you can see this in this little video here. Now, we won't necessarily be adding together waves which completely add together or completely cancel out. We can have intermediate situations too. So let's now mathematically consider what happens if we add together two waves which are absolutely identical in every way apart from their phase. So for the first wave, we can describe it by the normal sinusoidal equation. We can say y1 is equal to a sine kx minus omega t. So it's just a wave travelling in the positive direction. Now the second wave that we want to add to that first wave is identical apart from its phase. So it's described by the wave function y2 is equal to a sine kx minus omega t plus phi. And now to get the superposition of these two waves, we just need to add these two wave functions together. But in order to do that, we're going to need to make use of a trigonomic identity. So the trigonomic identity that we need to use can be written as sine A plus sine B is equal to 2 sine A plus B on 2 times cos A minus B on 2. So let's look now at how we can use that trigonomic identity to come up with an expression for what happens when we add together our two waveforms. Okay, so we're going to add together y1 is equal to a sine kx minus omega t and y2 equals a sine kx minus omega t plus phi. And so when we do that, we'll have y1 plus y2 is equal to A. We'll take A out as a common factor. It stands for the amplitude. And then we've got sine kx minus omega t plus sine of kx minus omega t plus phi. Now, in order to add together these two sine functions, what we're going to need to do is use the trigonomic identity sine of A plus sine of B is equal to 2 sine of A plus B on 2 cos of A minus B on 2. Now these A's are not the same A. The A here is the amplitude. This A stands for whatever's inside the sine function. So equating this to our expression here, we can see that this term here is going to be our A, and then this term here is going to be our B. So we'll need to work out what's A plus B on 2. So A plus B on 2 is equal to kx minus omega t plus kx minus omega t plus phi on 2. And so kx plus kx, that's 2kx, minus omega t, that's minus 2 omega t. And we're dividing all that by 2, and then we've got to divide the phi by 2 as well. So that gives us kx minus omega t plus phi on 2. And a minus b on 2 is equal to kx minus omega t minus kx minus omega t plus phi all over 2. So this kx and this kx will cancel out. Minus omega t minus omega t, which is plus omega t, will cancel out. And we end up with minus phi on 2. So now we can substitute these into this expression. So we've still got the A standing for the amplitude out the front. So we've now got y1 plus y2 is equal to, we've got a 2 and an A. So 2a sine of A plus B, kx minus omega t plus phi on 2 times cos of minus phi on 2. Now, there's another trigonomic identity that tells us that cos of any number, theta, is the same as cos of minus theta. So we can actually rewrite this as 2a. I'm going to start with the cos, and I'm going to replace minus phi on 2 with phi on 2. Sine kx minus omega t plus phi on 2. So now what we have is two parts to this equation here. This 2a cos phi on 2, this is, once phi is set for a wave, phi is the phase difference between the two waves, this is going to be some constant number. So this is going to be the amplitude of our resultant wave, our superposition. And then sine kx minus omega t plus phi on 2. This is just the travelling wave equation, and this time the phase difference is phi on 2. So the phase of this resultant wave is going to be the average of the phases of the two incoming waves. So this is just a travelling wave. So let's just work through a few different examples of different things that we may want to choose for phi. We could start by choosing the simple case where phi is equal to 0. That is, there is no phase difference between the two waves. The y1 and y2 are exactly identical. If we were adding together identical waves, we'd expect to get constructive interference. So we'd expect them to add together at every point. And so ideally we get a wave with double the amplitude of the first wave. So let's try out this equation for that case. In this case, we've got y1 plus y2 is equal to 2a cos of 0 sine of kx minus omega t, and this is 0. And cos of 0 is just 1. So this is equal to 2a sine kx minus omega t. We can look at a little graph of that now. Okay, so this graph down here shows us what we get in that situation. The blue and the green lines are directly on top of each other because we're adding together identical waves. and then the red line shows the resultant. So you can see the resultant has double the amplitude of either of the input waves. Okay, now let's look at another case where we've got 180 degrees or pi radians out of phase. So in this case, the waves are what's known as perfectly out of phase, and we'd expect them to cancel each other out everywhere. So substituting in, we've got 2a cos pi on 2 sine kx minus omega t plus pi on 2. Now in this case, cos of pi on 2 is equal to 0. So this should equal 0 everywhere. So we can look at another little figure of this one. So here's this figure, and you can see that when we've got a phase difference of pi, the two waves are perfectly out of phase. So when one's going up, the other's going down. And then the resultant is the red line along here. So the resultant is always equal to 0, as they're always cancelling each other out. So let's try one more. Let's consider what happens when phi is equal to pi on 3. In this case, we've got y1 plus y2, which is equal to 2a cos, now it's pi on 3 divided by 2, so that's pi on 6. Well, this is 30 degrees when that was 60 degrees. And this is sine kx minus omega t plus pi on 6. Okay, now we can evaluate pi on 6. If you know much trigonometry, you'll know about these little triangles that you can do. And so we've got 30 degrees or pi on 6 up here. And for this triangle, this side has length 2, this side has length 1, and this side here has length root 3. And so cos of pi on 6 is adjacent over hypotenuse, or it's root 3 on 2. Okay, so just substituting in for this, we've got 2a times root 3 on 2, so that is equal to a root 3 times sine of kx minus omega t plus pi on 6. So let's look at a little graph of this one as well. Okay, so I've put that up here so that it can be a bit bigger. And you can see that there's 60 degrees in phase difference between the input waves, the green and the blue one. And then the resultant one is given by the red. So the peak amplitude here is halfway between the two peak amplitudes for the two input waves, which is because we have this phi on 2 as the phase difference here in our equation for the travelling wave. Okay, so now you've been introduced to the principle of superposition, which tells you how to add together two waves. It's really powerful because after the two waves have passed each other, they just continue going on their way as if nothing had happened. So because the law of superposition works, it actually makes all of the physics problems a lot easier. We just need to add together the points on the waves when they overlap, and then just assume that they go on as they were to start with once they've passed each other.